Let's continue. So I want to look at an example here on the whiteboard. Okay, and the series is the series, the sum goes, it's an infinite series. The sum goes from n equals 1 to infinity of the nth root of 2. And I want to know if that series converges or diverges. Okay, we want to know if that series converges or diverges. Take a moment to copy it down. Okay, so how would we handle this problem? All right, well, let's take a look here. So we have the nth root of 2, and you know that the nth root of 2, okay, this is the nth root now. This is the nth root. Okay, we could write that as 2 to what power? Good, Jonathan. Good, Clea. 2 to the 1 over nth power. Okay, so we can write some terms out here. You know, 2 to the first power plus 2 to the half power plus 2 to the third power plus 2 to the fourth power. Okay, we can keep going. Now, of course, what we care about is how do the terms behave as n goes to infinity? This is the term of the series. Okay, and I want to know how that term behaves as n goes to infinity. So what would the limit of a sub n, the nth term, be as n goes to infinity? Two to what power? Two to the zeroth power. That's right, Jonathan. And what is 2 to the zeroth power? That's right, OPME. What is 2 to the zeroth power? 1. That's right. That's right. And so, and notice 1 is not equal to 0. 1 is not equal to 0. So what's happening is when n is large, the terms of this series here are essentially equal to 1. Okay, they're essentially equal to 1. They're not getting smaller. They're essentially equal to 1. And so by the test for divergence, what do we know about this series? Does it converge or diverge? By the test for divergence, okay, by the test for divergence, and I wish I had a little more room here. Let me see here. Hold on. I'll get myself some room. Hold on. Just need a little more room. Racer's much better on this new blackboard. That's right, Clea. That's right. Let me go back to blue. So, hold on. Sorry. Just have to erase. Just have to erase. Hold on. Where'd you go? Okay, hold on. All right. So, putting back what I had here. So, by the test for divergence, this series diverges. Okay, the terms of the series are not getting smaller. As a matter of fact, as n gets large, as you go out into the series, the terms are approximately equal to 1. So it diverges. That's right, Yonatan. The series diverges. Well, we got to be careful. Just because the terms of the series approach 0 doesn't mean the series is going to converge, because the harmonic series does not converge. But certainly if the terms of the series are not approaching 0, the series cannot converge. So it definitely would diverge in that case. Yeah, harmonic series always diverge. But this series here, which is just a series whose terms don't get smaller. So it can't converge. It can't converge. It's much easier to prove divergence than convergence, as a general rule. All right. Are there any questions on that? All right. Well, then let me bring up another problem here. Hold on here. Okay. Let me give you a moment to copy this example down. Okay, so this series is what's called a power series. Okay, it's what we call a power series. Okay, so if we were to write out some terms of the series, okay, well, first of all, this series could be written this way, right? We could write this series, we call it a power series because there's a variable x in there. So that power series can certainly be written this way. And what does this series remind you of? What does it resemble? I mean, you've seen a lot of different kinds of series now, or at least some series. That's right, Jonathan. It's a geometric, it should remind you of a geometric series with a common ratio of x over 3. So, well, a geometric series under certain conditions will have a sum, right? So let's go to the next page and look at the solution for this. So what I do in the solution is I try to write out some terms of the series, the first 4 terms, just so it's a little less abstract for you. Okay? Sigma notation is nice, but how many find it helpful to see some of the terms of the series written out, maybe the first 3 or 4 terms? How many kind of like seeing that? It makes it a little more concrete. Okay, Daniel likes that. Excellent, excellent. Okay, so this power series is a geometric series with a common ratio of x over 3. I mean, you could, again, you could show this. A1, here are the first 4 terms of the series. And if you were to take the second term and divide it by the first term, second term is x squared over 9. Divide that by x over 3. Okay, that's going to give you x squared over 9 times 3 over x, and that will equal x over 3. If you were to take the third term and divide it by the second term, third term is x cubed over 27, and you divide that by I can make a little room here. Okay, divide that by, so you have x cubed over 27 divided by x squared over 9. That's x cubed over 27 times 9 over x squared. And you get back, again, x over 3. Common ratio is x over 3. So we want to find then the values of x for which this series converges. So this is not like we do have a common ratio of x divided by 3, but that common ratio, the absolute value, for this power series to converge, the absolute value of the common ratio has to be less than 1. That means x over 3 has to be less than 1 and greater than -1. And if I take that inequality, okay, and I multiply through by 3 everywhere, I'll end up with x is less than 3 and greater than -3. And so this gives us what's called an interval of convergence. It gives us what's called an interval of convergence. Let me just clear the space here a little bit. Okay, so again, what I'm doing is I'm multiplying by 3 through the inequality, but 3 is positive, so the inequality sign doesn't change. So that means x is between -3 and 3. And those are the values of x for which that power series converges. Okay, and so when x is between 3 and -3, we have a convergent geometric series. So the convergent geometric series, the summation for the formula is a divided by 1 minus r. Well, a is x over 3. Okay, that's your first term. Let me see here. I gotta try not to write things to be a little bit neater. So a is x over 3, and the common ratio r is x over 3. And so this will give you then a summation of x divided by 3 minus x. You see, eventually we're going to be applying these series concepts to functions. And functions can be written as what are called power series. And power series have intervals of convergence. So in your section 7.2 series homework, you'll see some basic problems dealing with intervals of convergence and finding the sum of the power series for that interval of convergence. Any x value in this problem between -3 and 3 would give you a series that converges. So like for example, if I wanted to like let's say that if x were equal to say 2. If x were equal to 2, then the power series given by 2 over n over 3 over n, so I'm just substituting in x in here. Well, the sum should equal x over 3 minus x. So this would equal 2 over 3 minus 2, which is 2. You see? So you can use this formula to get a lot of different answers. If x were equal to 1, if x were equal to 1, well, then this power series formula says that the series, okay, given by 1 over n over 3 over n, that would just equal 1 over 3 minus 1, and that equals a half, you see? So it's like a formula you can use, and it's good for any values of x that fall inside the interval of convergence. Okay, are there any questions on that? All right. All right, well then let's look at another example. I want to look at another telescoping series problem. Okay, so I'm going to go to I'm going to go to this example here. Let me give you a moment to copy it down. Okay, take a moment. Yes, Jonathan, yes. Question?
Professor, you said for the previous problem you asked find the sum if it exists. We didn't find the sum. How would we find the sum?
Oh, we did. All right, hold on. Let me go back to it. We'll go back to that example class. Hold on. Okay, find the sum if it exists of the power series. So this here this is the sum right here.
The sum has a variable in it?
Sure. Yep.
All right then.
Yep. Yep. A power series, the sum has a variable in it. But you see, what we can do is we can put in different values for the variable. So like if x equals 1, that the power series would give us a half. If x were equal to 2, the power series, the sum would be equal to 2. It's like you get a formula that you can use for different values of x. But yeah, but it's still a sum. I mean, it's even though it has a variable in it, a sum. See, you like probably you are used to thinking of sums as like it has to be a number, but a sum could have a variable in it. Yeah, yeah. Good question. Good question. All right. All right. Take a look at this here. We're going to find the sum of this series. Now you notice that this series starts at n equals 2, but do not concern yourself with that. We still can, you know, that's not an issue at all. Okay. The starting index, we typically started at n equals 1 for a series, but you don't have to start at n equals 1. Okay. You don't have to. We can indeed, Clea, put the 3 in front. I like that idea. I like that idea. So we can write this as 3 times the summation, where n goes from 2 to infinity, of 1 divided by n times n plus 2. What kind of sum does this look like to you to be? It's not harmonic. It's not geometric. That's right. Good, Jonathan. It's a telescoping sum. And this will converge. This sum will converge. So just like the other telescoping sum problem we saw, we're going to do the same kind of thing. We're going to rewrite the nth partial sum. So let's go to the solution here. Okay, so here's the nth partial sum. And I'm going to factor the 3 out. And I'll worry about the 3 later. Right now, my attention is focused on the summation where I goes from 2 to n of 1 over I times I plus 2. So we're going to use partial fraction expansion to rewrite that summation. And I know you've done this many times, the partial fraction expansion, but I'll just put in a little detail here. So hold on here. So we'll multiply through the equation by the least common denominator, which is I times I plus 2. And you get simplification on the left and simplification on the right, and you arrive here. And then you, set up your equation. So you've done this before. You've done this before. And based on this equation, you have two variables, A and B, to solve for. Well, yeah, A and B. And so A plus B has to equal 0, and 2A has to equal 1. And so A is a half, B is a negative a half, and now you have your nth partial sum here. So let me give you a moment to catch up. Please let me know if you have any questions. Why do we have a minus at the end? It is A plus B. That's right. That's right. But A equals a half and B equals negative a half. So, we could think of it like this: A plus negative a half. This is your A. A is a half. And B is negative a half. Very good, Clea. All right, so good questions here. Good questions. Okay, so this is excellent. Very good participation. All right, and now that we've written the nth partial sum this way, we can write that nth partial sum. We can telescope it out. We can telescope it out. Now, what I'll do, also here, let me just see here one moment. That's not bad. That erases pretty well. Okay. Certainly, I can write this as 3 times the sum, where I goes from 2 to infinity, of 1/2 times 1 over I minus 1 over I plus 2. Right? So again, and I'm actually pleased that you're telling me really you want to pull those constants out. Okay, so it's just like with integration, nuisance constants, you want to pull them out and bring them in later. Okay, are there any questions before I go to the next page? All right, let's go to the next page then. So the nth partial sum, okay, the nth partial sum okay, we have it here, and hold on here. For I'm saying here I want n to be greater than or equal to 4, just because I need to have enough terms to see what the pattern pattern is. Remember, we're going to look at we're going to try to find an expression for the nth partial sum, and then let n go to infinity. But in order for me to sort of understand what's happening, I have to at least have four terms of the series of the partial sum. So now what I do is that the half here, I can bring that out front. So the 3 halves here is from 3 times 1/2. And now the summation over here, no, I want red, please. Thank you. The summation, I can expand it out as you see here. I can expand it out as you see there. So, like for instance, well, let me give you a moment to copy this. So I'm saying this telescoping series, all of the terms are going to cancel, except you're going to have a half plus a third minus 1 over n over minus 1 over n plus 1 minus 1 over n plus 2. Now you have to kind of convince yourself that that's true. Okay, and to convince yourself that's true, what I like to do is just sort of play around a little bit with terms. So, like for instance, if I were to do s sub 4, okay, if I were to do the fourth partial sum. Now this is, I'd like to kind of write it here because you can see all the terms there. S sub 4 is going to be a half minus a fourth. So this is now, what I'm doing here is just a separate thing. A half minus a fourth plus a third minus a fifth, okay, plus a fourth minus a sixth, okay? What cancels out? What cancels out on S sub 4? What fractions cancel out? The 1/4, that's right. So the fourths go out, okay, and you're left with a half plus a third minus a fifth minus a sixth. Okay, so look, a half plus a third, that's a half plus a third minus 1 over 4 plus 1 minus 1 over 5 plus 1. No, minus 1 over minus 1 over 4 plus 2. So the fourth partial sum, I have, the 1, the half, the third, okay? I got to be careful here. I mean, we mustn't forget the 3 halves, but I'm just trying to, we know there's a 3 halves. I mean, we know there's a 3 halves in front of this. I guess I can put that all in. Hold on. 3 halves times all of this equals 3 halves times all of this, which equals 3 halves. Hold on. Which equals 3 halves times all of this. Okay. So you see, you got the 3 halves. You have the half and the third, and then minus 1 over n plus 1. Well, n is 4. N is 4. And look, you have 4 plus 1. That's for the fifth. And then the sixth is 4 plus 2. So you see, what you can do is, and you could verify that this formula works for the fifth partial sum also. You could verify it. And it's sort of like you have to test a few partial sums out before you can figure out what the general formula is for the nth partial sum. You see what I'm saying? See what I mean? So this telescoping sum then is equal to what you see there. And so the nth partial sum, the sort of the final version of it is equal to 15/12 minus 3 halves times 1 over n plus 1 minus 3 halves times 1 over n plus 2. That's the nth partial sum. Okay? You distribute the 3 halves everywhere here. So, are there any questions on this? Any questions? What I have here, maybe I'll mark it in, well, yeah, I can mark it in green. So this part here, this is not formally a part of the solution. What I have here in green right here, I just wanted to show you how I can conclude, how I can deduce that this is the general formula for the nth partial sum. And now what do we have to do? Now that we have the general formula for the nth partial sum, what do we do? What do we do with this general formula here for the nth partial sum? What do we do with it? I want to find the sum of the series. What do I have to do with the nth partial sum? Take the limit, right, Jonathan, as n goes to infinity. That's right, and that's what I'm going to do. And when you take the limit as n goes to infinity, okay, as I did here, okay, this term goes to 0, this term goes to 0, and you're left with 15/12. So that's what your series equals. Your series equals 15/12. If you were to program this series in a computer and have it keep generating terms of the series and adding them and have it run for years and years and years, eventually you're going to get a decimal very close to 15/12. Okay, and so that's the answer. In my own career as a graduate student, I saw these types of series come up a fair amount. Not all the time, but you definitely want to have knowledge of how to deal with them, these telescoping series, when they come up. And this really, I think, summarizes section 8.2. What we've talked about so far, I think, will help you for the homework that's due on Monday. Of course, your exam, right, is due Saturday at 3:30, parts 1 and 2, and I mean the window of time. Again, I will let students complete the exam late, but it is a 10% deduction off their score. We have to be fair to the students that complete the exam on time, right? And this is really fascinating material. I mean, how many think this is pretty cool? What you're learning in section 8.2. Okay, Avery's liking it. Wonderful. A little complicated. Yonatan's sort of give or take. All right. All right. Well, on that note, if there are no questions, I'll stop the recording. And we've covered. I think what we've covered now will help you with your homework for section 8.2. All right. So I'll stop the recording.